Presented by Caltech.
So it's my very great pleasure to open the inaugural Robert F. Christie Lecture. One of the things that makes Caltech really special is that we don't have administrators. We have scientists and engineers who step up to serve their colleagues because they believe in them and they believe in this institution, and Robert Christie was such a man. He was a highly accomplished theoretical physicist who served Caltech as division chair, as provost, and as acting president. And the Christie Lectures were established to celebrate Robert Christie's life, his accomplishments, and his impact on Caltech. And this annual lectureship was made possible by generous gifts from Colleen and Harold Brown. Harold Brown, who recently passed away, served as Caltech's president from 1969 to 1977, and I, Juliana Christie, who is a Caltech astrophysicist and wife of Dr. Christie. And so, again, we're very pleased that Juliana and her family and friends are joining us for this evening. So now I want to turn to introducing our speaker, Kip Thorne. So it's a bit daunting in a short introduction to do justice to Kip's incredible and varied career, from his work in relativity, black holes, wormholes, and time travel, to gravitational waves and LIGO, to textbooks that are the standard references for physics students. In my day, the famous Meissner, Thorne, and Wheeler textbook on gravitation was known to all of us as the telephone book due to its sheer size. To popular books like Black Holes and Time Warps, to his post-faculty career advising on Hollywood movies like Interstellar. And however, since this is the inaugural Christie Lecture, honoring in part Christie's impact on Caltech, I thought I would limit my brief remarks to Kip, focusing on Kip's contributions to this institution. So Kip spent much of his career here, first as an undergraduate, class of 1962, then as a professor, starting in 1967, with a very brief stint at a small private institution in New Jersey in between. So the Caltech physics faculty is relatively small compared to the institutions that we consider to be our peers. So we have to choose our areas of research very carefully. And during his time at Caltech, Kip set out to build Caltech as a premier institute with a program in gravitational wave science, both instrumentation with what became LIGO, and later in numerical relativity, which involves the calculations that are required to understand signals produced by merging black holes and neutron stars. So when he started his efforts in the 1970s, gravitational research wasn't even really a field of physics. It was quite unclear if there were detectable sources of gravitational waves. If there were, it was not clear that they would be possible to detect. And Kip took this vision and built a program at Caltech by carefully recruiting excellent people to join him. In the early days, people like Ron Drever, Stan Whitcomb, and many others. And so I have to say, Kip maintains this ephemeral theorist profile where he likes to think about things like wormholes and time travels. But after I joined the faculty, I had the opportunity to watch him firsthand as a formidable force, as a leader, and dare I say, Kip, an administrator. Why do I say this? Well, Kip would watch very carefully for the opportunity when the time was ripe to hire a new faculty member, either in experiment or in theory. And he would launch an extensive search, sometimes spanning many years. He was organized, meticulous, thorough, critical, and convincing. And that's how we ended up with experimental faculty working on LIGO, like Rana Adhikari, and theory faculty like Yanbai Chen. And this arguably makes Caltech the premier institution in experimental and theoretical gravitational wave science in the world, with a small number of faculty. Kip also influenced generations of Caltech undergraduates and PhD students. He was mentor to some 53 PhD students, which is pretty remarkable. He won the ASCA Teaching Award, the Graduate Student Council Mentoring Award, the J.D. Jackson Award for Excellence in Graduate Education, and, very importantly, he and his wife Carol Lee offered their home near the Rose Bowl as a base to Caltech undergraduate pranksters. The last of these pranks was now a few years ago, and it involved some hundreds of thousands of LEDs turning on the hillsides above the Rose Bowl after the football game, turning it into a Caltech sign. So, as you can see, Kip's contributions to Caltech have indeed been profound. And then, of course, there's his scientific legacy. He's been honored by so many awards that it would take me half of the time allotted to list them all, but of course, culminating in the Nobel Prize in Physics in 2017. And so without further delay, I'd like to invite Kip to deliver the first Christie lectureship. Kip?
Thank you, Fiona. Robert Christie, or Bob as I called him, was a dear friend and colleague of mine, and a man whom I greatly admired. So it's a great honor to be the first Christie lecturer here at Caltech, and it's a doubly great honor because this lectureship was endowed by Juliana Christie, who is a very dear friend of mine as well, and by Harold and Colleen Brown, whom I was very fond of and admired during the period when Harold was the president here at Caltech. I admired Bob himself for his profound contributions to theoretical nuclear physics and to theoretical astrophysics, both, for his deep insights and his leadership in those fields. I admired him for the fact that after being the genius who figured out how to make the first implosion bomb work that ended the Second World War, he then devoted decades of his personal time and energy and expertise, together with Japanese colleagues, to understanding in depth the effects of the radiation on the 100,000 survivors of those explosions at Hiroshima and Nagasaki. I admired him for his leadership at Caltech as provost under both Harold Brown and then later Marvin Goldberger, and as acting president. And I'm going to give you an example of that leadership, his tremendously important contribution to making gravitational wave science take off, not just at Caltech, but in the world. But before I get to that, let me give you a little bit of personal history. This is actually going to be a talk that is sort of retrospective on my career. I thought that this might be the last talk I ever give in Beckman Auditorium, so if you'll indulge me, I think that's what I'm going to do. Before I was 8 years old, growing up in Logan, Utah, I wanted to be a snowplow driver because the snowdrifts were taller than my father was tall, several times taller than he was, particularly in the winter of 1948. But then when I was 8 years old, my mother took me to a lecture about the solar system, and I fell in love with astronomy and immediately switched allegiances. I was going to become an astronomer. And I did astronomy projects for the next few years under my mother's prodding and inspiration. And then I have this wrong. I don't know how I wound up with 48 at age 8. It was in 1953 at age 13 that I picked up in a used bookstore in Salt Lake City a copy of George Gamov's book, 1, 2, 3, Infinity. George was a theoretical physicist and cosmologist at the University of Colorado, an emigre from Russia, and his book described how the laws of physics control the way the universe works, and what their profound influence is on the universe. And immediately I decided I'm going to be a physicist, but I'm going to work on astronomical issues. And so here I am, all these decades later. And that's the story of my career. In 1955, at age 15, Time magazine, which came into our home every week, had a cover article about Caltech with Lee DeBridge, who at the time was the president of Caltech, on the cover. I read it intensely and just totally fell in love with the idea of Caltech. It described an institution where if you were taking an examination and you got the wrong answer for some question, but your reasoning was really good, then you could get a high mark. And I thought that kind of place that's the place I want to be. And so I struggled hard to get into Caltech, did everything I could to optimize my chances of getting in. I did get in. I arrived here in 1958 and quickly discovered that my mind worked more slowly than most any of my colleagues. And when we were comparing IQs, I kept my mouth shut in the bus on the way to freshman camp orientation. I didn't hear an IQ that was quoted that was within 10 points of mine. They were all higher. Now, I can imagine that some of them may have been inflated, but as things went on, it became clear to me that I was not as sharp or as quick as my colleagues. And so I struggled for the first year and a half, but that meant that I had to develop ways to come to understand things and learn things more thoroughly than my compatriots in order to keep up, because I was doing it so much more slowly. And so that's what I did. I also discovered that my memory was much worse than theirs. And some years later, I learned that the only person in the field whose memory was worse than mine was Richard Feyman. And then I came to understand from that if you have a lousy memory, then you have to get really good at figuring things out so you can figure things out again and again and again because you didn't remember them. And it's it makes you into a real powerhouse in physics. Well, I'm not the powerhouse that he was, but at least I made use of that physical disability that he and I shared. After about a year and a half at Caltech, I thrived as I had begun to develop my ways of dealing with my studies, and I came to love Caltech just as much as I had expected to. In 1962, I went to Princeton for graduate study. I went there because John Wheeler was there, and John Wheeler was working in relativity theory. He was the guru of relativity theory. I was told by Jesse Greenstein, who was my principal mentor here at Caltech, with whom I worked and whom I admired, that relativity was not going to be important for anything in this universe except the expansion of the universe, and I shouldn't spend my time on it. Fortunately, I didn't. I learned a lot from Jesse in other ways, but I didn't take his advice on that. I went and I worked with John Wheeler, and from John I learned about the warped side of the universe. This is my own phrase for objects and phenomena that are made from warped space and time, including black holes, gravitational waves, wormholes, and time travel, the topics I'll focus on this evening. In 1966, I returned to Caltech and I built a research group working on the objects on the warped side of the universe. And I, in this research group, set the vision for where we were going, set research problems for students, but my students and my postdocs really did the great research. And if you look at all of the research that my students and postdocs did while they were at Caltech in my group, it is as a sum total far greater than my own personal achievements, and I take great pride in that. My group was large. I had 6 PhD students and 3 postdocs right from the outset, and many, many visitors. And this is a photograph taken several years after I came on the faculty. This was about half of these people are my members of my research group, and half are visitors. Now, how could I fund such a large group right from the outset? The key is that Caltech is dedicated to help faculty realize their dreams and their potential, and through the faculty, help the students realize their dreams and their potential. And in the case of Caltech, of me, the key person on the faculty who helped me with the necessary funds to take off on such a research group was Willie Fowler. Willie was just in the late stages of doing the research that would get him the Nobel Prize himself, and he was also beginning to wind down his work in theoretical astrophysics, what we came to call relativistic astrophysics, as I was ramping mine up. And so I went on to his NSF research grant, as did all of the vast number of students and postdocs that I was acquiring. And then after about a year or two, he just made me the PI on that research grant from NSF. And I continued that research grant through to the day that I retired about 10 years ago. And I did the same with Yanbei Chen, who was my successor. And so you have this research grant that went from Willie to me to Yanbei Chen. Obviously, it would not have continued if I hadn't done some decent work and if Yanbei weren't doing some decent work. But this was key to pulling this off. A fellow faculty member giving me a big hand up in being able to build the group that I needed. Another source of funding that was absolutely crucial to me throughout my career was from Walter Burke and the Sherman Fairchild Foundation. Walter very quickly became a close friend of mine in the early 1970s when he came to Caltech to examine us to see whether or not the Sherman Fairchild Foundation should invest in something called the Sherman Fairchild Scholars Program here. And so I met him, I talked with him about Caltech. I was a young faculty member. I shared with him my dreams, and one of those dreams was to bring Stephen Hawking here as a Sherman Fairchild Scholar. And I think that helped play a role in our getting the program. Stephen did come as a Fairchild Scholar and came back time and time again as a Fairchild Scholar, supported by Walter, by the Foundation's funds. So that gives you some sense of how I took off in building a research group. Now let me talk about black holes, and then gravitational waves, and then the more speculative things of wormholes and time travel. What was known about black holes in 1966 when I arrived on the faculty? Well, we knew that if you have a heavy star and it exhausts its nuclear fuel, it may implode, get smaller and smaller and smaller and smaller. We use the word collapse rather than implode. And ultimately, it would become so small that gravity would become so intense at its surface that time would slow to a halt right at its surface. The gravity would be so strong that nothing could escape from its surface. And we called that a collapsed star, or in Russia, they called it a frozen star. But we didn't have, these were not very good names. It was not until 1968 that John Wheeler would coin the phrase black hole to describe it. And that phrase stuck when he first started using it. Now, black hole has the strange property, the circumference around the black hole is much smaller than its diameter. And you might ask, how can that possibly be? Well, if you take a child's trampoline, a sheet of rubber on high stilts, and you stick a very heavy and dense rock in the center, so the rubber sinks down like that. And if you then pretend that you're a blind ant, you have a degree from Caltech, so you have a lot of skills at measuring the universe you live on. This is your universe. You go march around and you measure the circumference of the universe, and then you measure the diameter, and you march and march and march. It's a very, very long trip. The diameter is obviously enormous compared to the circumference. You and I, looking at the diagram, know why. But as a blind ant, you figure it out because you're real smart. You're from Caltech. You figure out that the universe you live in is warped. Space is warped. And you figure out the details of the warping. Now, precisely the same diagram describes a black hole. And if any of you wonder, yes, these are precisely the same pictures that I drew by hand decades ago for a lecture that I gave here, but I don't think there are probably very many of you here who are old enough to have been to that lecture decades and decades ago. So yes, I'm reusing them. Okay. So it's the same diagram, but now this is the curved space inside a black hole. Take an equatorial slice through the black hole and imagine embedding it in a higher dimensional flat space, which physicists sometimes call the bulk. So I've written the bulk here. And the circumference is small compared to the diameter, and that is the shape of space around and inside the black hole. The black hole, of course, also has the property if things fall in, if you fall in, or if I fall in, here I am falling in as a little two-dimensional Kip on the surface of this surface. Remember, I'm only taking a two-dimensional slice to the black hole, so this is what space looks like on a two-dimensional slice. So I fall in on this two-dimensional equatorial slice. sending signals by a microwave antenna back to you on the outside. When I fall past something called the horizon, gravity is so strong it pulls the microwave signals down together with me down into what was the rock but is now a singularity where gravity becomes infinitely strong, curvature of space becomes infinitely strong, and things, everything, including time and space, are destroyed. And we don't understand this singularity, but it's governed by the laws of quantum gravity, which we also don't understand very well. So this is the warped space of the black hole, and time is also warped around the black hole, so that as you go down near the horizon, if you hover just above the horizon, time slows to a halt compared to time back here on Earth. If you go inside the horizon, what is slower than stopped time? Well, time flows in a direction that you would have thought was a space direction. It flows down toward the singularity, and that's one reason that nothing can get out of the black hole. Nothing can flow backward against the local flow of time. If you have a time machine, if time machines are allowed, you don't do it by going backward against the local flow of time. You have to do it in some other manner, and I'll very briefly discuss that later. General relativity also predicts that space, that if a black hole spins, then space is dragged into a whirling motion like the air in a tornado, a fast spin of space near the horizon, much slower farther away. And this whirl of space then is the third of three aspects of the warped space-time of a black hole: the warping of space, the warping of time, and the whirling of space caused by the black hole's spin. This is a precise depiction of the warped space-time of a fast-spinning black hole. So here is that warping of space. The horizon is right here, where it's black. It looks like a circle, but that's because I have taken only a two-dimensional slice through the equator of the black hole. That circle will be a sphere if I add the third dimension in. There is then the color coding shows the slowing of time, where it's yellow time is flowing at 10% of the rate that it is far away, and the white arrows show the angular velocity of dragging of space into motion around the black hole, or the so-called dragging of inertial frames. So much for what we knew in 1966. Now let me turn to the golden age of black hole research, which spanned the period of my graduate studies at Princeton, really took off after I arrived back at Caltech. The thing that more than anything else I think triggered this golden era of black hole research was the discovery by Martin Schmidt, a dear colleague of mine here at Caltech in 1963, of quasars. What Martin did was he identified the source of light that corresponded to a radio source that radio astronomers at Caltech had been studying. Identified the source of light and measured the spectrum of the light and discovered that the wavelength of the light in the spectrum was pushed by 16% to the red compared to the normal wavelengths of these lines in the spectrum. And he thereby concluded that the source here, this object, was receding from Earth at 16% of the speed of light. He argued that this was probably a recession, a motion away from Earth due to the expansion of the universe, which it did turn out to be, and concluded then that this star-like object was 2 billion light years from Earth, and the luminosity, the light coming off of there, was that of 2 trillion suns. Enormously bright. The only thing hugely brighter than that is the gravitational wave sources that LIGO has seen, and I'll return to that a little bit later. In December of 1963, there was a conference then in Dallas, Texas, of astronomers and relativity experts to try to understand what these objects could be, these quasars. And by the end of the conference, there was pretty much a consensus that there was no way that anything except gravity could be responsible for the enormous power output of these quasars. This very actually compact object with enormous power output. Only gravity could produce that power, and it would have to be the gravity of what we now call a black hole. At the time we were calling collapsed stars, a supermassive black hole, what turned out to be a 2 billion solar mass black hole or collapsed star. But it was not at all clear at the time how quasars were powered. We just were pretty convinced it had to have to do with black holes. And so research on black holes took off, theoretical research. It had already been spurred by my PhD thesis advisor, John Wheeler. And by 1971, a set of colleagues of mine in Canada and England had proved that an amazing thing about black holes, that all the properties of a black hole are fixed by just two numbers, the mass of the black hole and its spin, that is, its spin angular momentum. And if you knew the mass and the spin of the black hole, you could compute everything else about them, including all the details of this warped space-time in this diagram. Johnny Wheeler coined the phrase, "a black hole has no hair," for this, which very quickly caught on. And then there was the question, how does it lose its hair? Remarkably, Richard Price, a PhD student of mine, explained how it lost its hair at the same time as my colleagues were proving that black holes are hairless, that all these properties are fixed by the mass and the spin. What he managed to show in his PhD thesis in 1971 was that if you disturb a black hole, then it will vibrate, it will shake around, sending off gravitational waves, ripples in the shape of space and time into the external universe, and those gravitational waves will carry away all of the hair. They will carry away all of the distortions of the black hole, leaving it in precisely the form that is predicted by its mass and its spin. That was a real tour de force. I was really proud of Richard. And then there was Saul Tucholsky, who is now on the faculty here at Caltech. He was also a student of mine. In 1972, he developed an elegant and powerful mathematical description of disturbed black holes. What is called the Tucholsky equation, one of the most famous equations in all of relativity to this day, he developed in 1972 to describe every kind of disturbance that a black hole might experience. And then there was the question, which we were all worrying about, are black holes stable, or could some of them self-destruct? Subramanian Chandrasekhar, who would a little bit later get the Nobel Prize jointly with Caltech's Willie Fowler, he was a frequent visitor to our research group, and he and I made a bet because he was quite convinced that if a black hole was spinning sufficiently fast, it would self-destruct. And so we made a bet on that, among the first of the bets that I have made, bets that have become somewhat famous since then. You can see all my bets hanging on the wall outside my office in Cahill. And he bet that he even pinned down a particular spin, at which spin the shape of the black hole changes in a weird way, according to the predictions of general relativity. He was pretty sure that if you spun faster than that, the black hole was spinning faster than that the black hole would self-destruct. So Saul Tucholsky had the mathematics in a powerful form for solving this, the Tucholsky equation. He sat down together with Bill Press, a compatriot of his, and the two of them together proved that all black holes are stable. If you went all up to the maximum spin that a black hole could possibly have, if the spin was higher than that, it wouldn't be a black hole anymore. It would lose its horizon. Everything below that, the black holes were stable. So how do black holes power quasars? By 1972, there was a consensus building that accretion disks were the likely mechanism. Disks of hot gas, perhaps produced when a star is torn apart by the gravity of a black hole, forming a hot disk that radiates very strongly off of the energy that is released as the gas gradually spirals in closer and closer to the black hole, releasing huge amounts of gravitational energy. That's where the bright light, the 2 trillion solar luminosities of light was coming from. And so naturally, with this consensus coming into play, I sat down together with my student Don Page and a Russian colleague, Igor Novikov, and we developed the mathematical theory of accretion disks around black holes. And having done that, we were in a position to solve a problem that people had really been concerned about. And that is that the gas from an accretion disk, as it goes closer and closer to the black hole and then goes into the black hole, it spins the black hole up until it's spinning faster and faster and faster. And it appeared from calculations by Jim Bardeen, who was, I think at the time, a student of Richard Feynman's. It appeared that as the gas spun the black hole up, after just approximately doubling the mass of the black hole from the accreting disk, it would get spun right up to that maximum spin where it would lose its horizon, and it would no longer be a black hole, and something strange would happen. And so we now had the full details of accretion disk, and we sat down and calculated it out and found a very strange thing, that as the black hole gets spun up faster and faster, it begins to capture radiation, light, X-rays, gamma rays coming off the disk, capture it in just such a manner as to spin the black hole back down. And the closer it got to that maximum spin, the more powerful it grabbed the radiation to spin itself back down. And it got buffered right into a spin of 0.998 of the spin that would have destroyed the black hole's horizon. And so to this day, it is generally thought that black holes don't spin faster than that. Now, in the movie Interstellar, the black hole spins a lot faster than that, and I'm responsible for that. But the rule of the game in the movie Interstellar was that we allowed ourselves to do anything the laws of physics permitted, but you would have to do some very careful tuning to avoid this kind of a limit. And so this is permitted, but it would probably not actually occur in the astrophysical universe. But anyway, so this was the maximum spin we found. How were the jets produced? The key answer to this, or one of the answers, the most beautiful answer, came from Roger Blandford, whom we hired at Caltech shortly after he did this work with Roman Znayak in Cambridge, England. In simple terms, you have an accretion disk of hot gas, and it pushes a magnetic field onto the black hole and won't let the magnetic field back off. These magnetic fields, then, as the black hole spins, they get twisted up, and then plasma, hot gas, hot electrically conducting gas, gets flung out along this spinning magnetic field. Now, that looks very simple, but in fact, when you recognize that the black hole is made from warped space and time and not from matter, then you have to ask, how does it grab a magnetic field? And when you recognize that it's not just a magnetic field out there, it's a magnetic field and electric fields and electrical current flowing, and there's such intense electric fields that the vacuum is breaking down and electron-positron pairs are being created. It's a real mess. Then the theory becomes much more complicated, but still quite elegant. And Roger Blandford and Roman Znayak built on work of Peter Goldreich on the theory of pulsars here at Caltech in doing their work. And then after they had devised the full explanation for how this jet is produced in this manner, including taking care of the issues that I described to you, the theory was elaborated by Sturl Finney and then by me and my students in a book that we wrote on the whole subject called Black Holes and Membrane Paradigm. And it is remarkable then that Roger Blandford, Peter Goldreich, Sturl Finney, and I became the professors here at Caltech in what we called TAPER, Theoretical Astrophysics Including Relativity. And it was so wonderful through my whole career having these great astrophysicists here by my side, be able to just go down the hall and talk to them about the problems that I was working on. Now, what would a black hole look like to your eyes if you had it up close? So you can understand this by imagining that you have a star here, and the star sends light ray to the camera, and the light can come to the camera along this path, or along that path, or along this path, looping around the black hole. So that star produces 3 images around the black hole shadow. Oliver James, who worked with me on the movie Interstellar and was the chief scientist at the Double Negative team that got the Academy Award for visual effects in Interstellar, he wrote a computer code based on the equations that I gave to him to compute then what will it look like if you have a very fast spinning black hole at this point 998 of the maximum, and the camera that is in orbit around that black hole. And this is in high resolution is what it would look like. And it's really quite amazing to see. This is called an Einstein ring, and there's a whole bunch of Einstein rings down here. And images of stars are created and destroyed along this Einstein ring, very quickly created and destroyed in pairs. And it's just quite marvelous to see. But that's not the black hole that you see in the movie Interstellar. In the movie Interstellar, the black hole looks like this. And why? Well, it's very easy to understand. The black hole in Interstellar has an accretion disk, a thin accretion disk. Light rays from the top back face of the accretion disk are pulled up over the black hole and down to the camera, And that produces this top piece of the image because the camera thinks that the back face is up here. Light rays from the bottom back face come under the black hole and up to the camera, which produces that piece of the image because the camera thinks the bottom back face is down there. And then light rays from the front of the disk go to the camera and produce the crossbar. So it's very simple to see. Now, it's quite remarkable that there is a gigantic black hole, about 4 million solar masses, at the center of our Milky Way galaxy. These are orbits of stars around that black hole as measured by Andrea Ghez and her team at UCLA. And the black hole is quite obviously down in here as the stars go whirling around it. That big black hole will be imaged with radio telescopes, something called the Event Horizon Telescope, very possibly for the first time this year. If not this year, then next year. It's a project that combines data from many radio telescopes worldwide, and these are all combined to make one image, and the image of the accretion disk around that black hole, probably a thick disk, so it'll look somewhat different from what you see in the movie Interstellar, and the shadow of the black hole. By autumn 1974, in autumn 1974 and through summer 1975, Stephen Hawking came to visit us at Caltech as a Sherman Fairchild Scholar, and our research groups merged together, and this is actually our merged research groups. Most of the research was on Hawking radiation produced due to quantum effects near the horizon of a black hole, which Stephen had just recently discovered. But with him there, I had the luxury of turning the leadership of our merged group over to him so I could focus on a new direction of research, and that was gravitational waves. Going back in time, gravitational waves were predicted by Albert Einstein. They consist of a stretching and squeezing of space, depicted here by imagining having a bunch of particles just floating out in space, being stretched and squeezed back and forth by the passing gravitational wave. The first person to attempt to detect gravitational waves was Joseph Weber at the University of Maryland, and he had the guts to try to do this, despite the fact that Einstein had said these waves are so weak that humans will probably never see them. He had the guts to try because there had been new insights. We had learned about black holes and neutron stars, which were very good sources of gravitational waves compared to anything Einstein knew about in 1916. And we had new technology, lasers and computers and so forth. So, inspired by Joe Weber and inspired by what I learned from John Wheeler at Princeton, I and my research group began building a vision for gravitational wave astronomy. And the vision was based on the fact that the laws of physics predict there are only two types of waves that can travel across the universe, bringing us information about what's far away. Electromagnetic waves, which includes light, radio waves, X-rays, gamma rays, and so forth, and gravitational waves. Galileo started modern electromagnetic astronomy 400 years ago when he built a little optical telescope, pointed at Jupiter, and discovered Jupiter's 4 largest moons. What we wanted to do was build gravitational wave telescopes and do for gravitational waves, the only other kind of wave that astronomers had any possibility to use, do what Galileo did. And this then was the obvious goal of gravitational wave astronomy and the foundation for the vision. I'm going to skip over this, but I just want to say that electromagnetic waves and gravitational waves are tremendously different in many, many respects. And as a result, we expected that many gravitational wave sources would never be seen electromagnetically, and the gravitational waves will bring us huge surprises. At the same time as my students and I were developing a vision for gravitational wave astronomy, Ray Weiss at MIT was inventing a new kind of gravitational wave detector. He said, let's take 4 mirrors and hang them from overhead supports. We're looking down on the mirrors here, so the wires are pointing out toward you. And we'll send a laser light in and split it in 2 at a beam splitter. Half the light goes in and gets trapped, bouncing back and forth between these mirrors, and half goes in there, bounces back and forth. Then the light comes back and recombines at the beam splitter, and a little bit of it goes down toward a photodetector down here. Most of it goes back toward the laser. If a gravitational wave comes by, it will push these mirrors apart and push those together, and as a result, change the interference of the beam splitter and increase the intensity of the light going toward the photodetector. If these mirrors are pushed together and those apart, then the intensity going toward the photodetector will decrease. So the technique of interferometry is used between these two arms to see the gravitational wave, and so we call this a gravitational wave interferometer. I looked at some numbers associated with this before I had read his paper. John Wheeler, and Charlie Misner were in the final stages of finishing off a textbook that we were writing called Gravitation, and that we were about to submit to a publisher for publication. I didn't have time to talk to Ray. I didn't have time really to study his technical paper, but I looked at some numbers and I put a very mild statement in here. This is not a promising approach. Let me explain why. What I really meant to say is this is crazy. Ray has lost his mind. Let's begin with 1 centimeter. Divide by 100, you get the thickness of a human hair. Divide by 100 again, you get the wavelength of the light that Ray wanted to use. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, the diameter of a nucleus of an atom. Divide by 100, you get the magnitude of the mirror's motions. It's about 1 trillion times smaller than the wavelength of the light that Ray wanted to use. That's crazy. It's crazy. And then, having put my views on paper in this textbook, which we never ever revised, you can go read the not promising pronouncement. I studied Ray's paper in detail. I talked with him, I talked with colleagues elsewhere, and I became convinced that this did have a shot at succeeding. And I made a decision that I and my research group would do everything we could to help the experimenters pull this off and succeed in detecting gravitational waves and creating gravitational wave astronomy. So my first step was to try to convince Caltech to create a research group working in gravitational wave experiment. I made a proposal to the physics and astronomy faculty. They bought it with enthusiasm. The administration bought it. I was even invited to make a presentation to the trustees. The trustees were not supposed to weigh in on it and didn't weigh in on it, but they expressed personal enthusiasm as well. This was quite a contrast with Ray at MIT. Ray could not find a single colleague on the faculty at MIT who thought that what he was doing made any sense. They all had the same reactions I did initially, but none of them went in and really studied it to see what the possibilities really were. He could not get any funding from the MIT administration, and he couldn't get any funding from the National Science Foundation for this. And so he was sort of stymied and went off and started focusing instead on studies of the cosmic microwave background radiation and became one of the pioneers of that field as well as of this field, but just by default because he couldn't get support at MIT to get into this game. At Caltech, we brought Ron Drever from Glasgow to lead the effort once the whole community had bought in. And he had the clever idea, well, a courageous idea is a better way to say it. It's a fairly obvious idea, but it was technically much more difficult than Ray's approach, that he would make those light beams in the arms of this gravity wave detector overlap so that each arm behaves like what we call a Fabry-Perot cavity. And then this whole instrument could become much more versatile, it turns out. And so this was one of a number of clever inventions that he was making at the time that convinced us we should bring him here. Then there was the issue of money. NSF was not sinking any money into this area, not willing to. MIT was not sinking any money in. Bob Christie, as provost, who had the primary responsibility, in consultation with the division chairs at Caltech and the president, he made the decision that Caltech would sink about $2 million of its own private funds into getting this off the ground at Caltech. And when you look at the inflation rate since that time, this was 1979, I think, this is a huge amount of money by academic standards. Once Caltech had gone in and made that commitment, that helped trigger major NSF funding. And ultimately, about 10 years later, MIT started embracing the project. A key next step was to bring Stan Whitcomb to Caltech from Chicago. And Stan became really the intellectual leader, hands-on leader of the effort at Caltech. He became later the chief scientist of the LIGO laboratory, and has really been, perhaps in the long run, he and Ray Weiss were probably the most influential experimenters working on the project. So at Caltech, Stan Whitcomb, under the aegis of Ron Drever, led the construction of a 40-meter prototype gravity wave detector. At MIT, Ray now had some funds from NSF. They completed the 1.5-meter prototype there. But more importantly, at MIT, they, together with a contribution from Stan Whitcomb, did a feasibility and cost study for kilometer-length interferometers. And with that in hand, MIT and Caltech, with encouragement from NSF, created the LIGO project, led by a troika of Ray Weiss, Ron Drever, and me. We three were the most dysfunctional leadership that science has ever seen. Well, at least that physics has ever seen. I don't know enough about other fields, but that physics has ever seen. And so, inevitably, in 1987, we brought on Robbie Vogt, who had been the first chief scientist at JPL and had been the provost at Caltech. We brought him on to direct the project. He knocked heads together between the Caltech and MIT groups, which were not really collaborating decently, turned this into a true collaboration. He built a strong engineering team to go alongside these physicists, paired the physicists with the engineers, developed conceptual design for the LIGO facilities, the vacuum system, and the initial gravity wave detectors, the initial interferometers. And he did a realistic costing of what it would cost. And then on this basis, we proposed in 1989 the construction of LIGO. First the facilities, and then in 2 steps, we would build initial interferometers that were essential in getting our feet wet with big interferometers and see what the problems were, but would probably not be good enough to see anything. And then with what we learned from the initial interferometers, build advanced interferometers, which would very likely see a lot of gravitational waves. In 1992, notice a 3-year gap, we got approval and first funding. And the problem was Congress. We had a battle against some very eminent astronomers who could not understand the culture that you would build at a cost at that time of about $200 million, $230 million if I remember what we were asking. At that cost, build a set of interferometers that wouldn't see anything. They're just a test bed. And you have to build a second generation in order to see it. And so we had a battle in congressional committee, and it took 3 years to overcome that. It was not Caltech astronomers who were fighting it. It was eminent astronomers from that little institution on the East Coast. Not MIT. Anyway. So we finally got the approval and first funding from Congress in 1992. And from that point onward, we had strong backing from Congress as well as NSF year after year after year with no significant budget cuts until we saw gravitational waves over a period of something like 25 years. And it was because we told them, this is hard and it's going to take us 2 generations, and just be prepared for that. So we had a 3-year battle to get the funding, but having been totally honest about how difficult this was going to be, we had full backing. And when we finally saw gravitational waves, the Republicans and the Democrats, both in Congress, took huge pride in having backed this project. So that was all under Robbie Vogt. In 1994, as we moved toward construction, we brought on Barry Barish, another Caltech faculty member. And here I want to remark, this has been a key aspect of Caltech. When we had needs for leadership, colleagues who were here at Caltech stepped up and met those needs. First, Robbie Vogt, then Barry Barish came in. Barry really organized how to do the details of the construction, and he then created the LIGO scientific collaboration. He expanded LIGO, so instead of 2 institutions, and what by the time he took over was something like 40 or 50 scientists and engineers, There were something like today 80 institutions in 18 nations with about 1,200 scientists and engineers. Why so many? I mean, for gosh sakes, why do you need so many? I can just explain it by saying you're measuring those tiny, tiny motions in the presence of all kinds of things that can go wrong. So many things that can go wrong that the instruments that are now operating, each of them has 100,000 data channels coming out, each data channel telling you about things that could go wrong either inside the instrument or in the environment. Tremendously complex, and to build these complex instruments, design and build them, required a very big team to pull it all off. From 2000 to 2010, we built the initial interferometers and ran them. Didn't see anything. And Barry was stolen away by the high-energy physicists from the community from which he came onto LIGO to lead the design study for their next generation of particle accelerators. And we brought in then a new director, Jay Marks, a really great director, to carry us through this phase of the initial interferometers and the beginning of installing the advanced interferometers. And David Wrightsey then took over as we were moving the advanced interferometers along. And David Wrightsey is our current superb director. And that's another really great thing about Caltech, the care with which the institution, which means the leadership of the administration, put into helping us find the right kinds of directors to really pull this off. And why was Caltech doing this as the lead institution? Because MIT would not buy in the early years. And so Caltech stepped up to the plate. And so here we are. This is Caltech as the headquarters of LIGO. Just a few photos of advanced LIGO as seen from the air, the vacuum systems inside which the mirrors hang. A baseball player put here by Barry Barish. He thought that would be more humorous than putting a LIGO scientist there. And a mirror hanging from an overhead support. In the meantime, my own theory students and postdocs were contributing in major ways to this. Alessandro Buonanno and Yanbei Chen found that the mathematical theory of how these advanced interferometers worked was wrong. It had not properly taken account of the quantum mechanical behavior of the mirror, something that seems awfully esoteric, or the proper account of the quantum mechanical behavior of the light. So they developed a correct mathematical description, which then required some redesign and re-optimization of the advanced detectors. Others of my students studied the noises and how to control them, and studied gravitational wave sources and data analysis techniques. Major contributions were coming from Vladimir Braginsky's group in Moscow, Russia. In 1991, when the Soviet Union crumbled, we were facing the loss of that Russian group, which was really absolutely a crucial group for some of the things we were doing. So Robbie Vogt, as LIGO director at the time, took private Caltech funds that he had control over, and his discretionary funds, and supported Braginsky's group for about a year and a half, until we managed to get funds from George Soros to support the group and hold it together. And then by then we managed to find a way, with the help of Stan Whitcomb, to get NSF to actually support Braginsky's group in Moscow. And there was enormously important technology transfer from Moscow to Caltech and other institutions in the LIGO scientific collaboration. Through that whole period, the Russians never knew that this technology transfer was going from east to west. It was under the radar of the Russian authorities. One of the most important things that Braginsky did was he told us that we were going to have to deal with the fact that these mirrors in LIGO behave like quantum mechanical particles. The LIGO instrumentation is designed to measure the motion of the center of mass of the mirrors, not just where the faces of the mirrors are. And we would be in LIGO, we will be monitoring the motions of 40 kilogram mirrors to a precision of 10 to the minus 19 meters in advanced LIGO. And that is the level of the quantum fluctuations of a 40 kilogram particle. An electron inside an atom jiggles around a level of 10 to the minus 10 meters. This is a billion times smaller because the particle is so much bigger, a 40 kilogram particle. And so these quantum fluctuations had to be dealt with. For the first time in advanced LIGO, humans would see human-sized objects behave quantum mechanically, and quantum non-demolition technology had to be developed to deal with this. This became a collaboration between Brzezinski's research group and my own research group, and it continues as such, although Brzezinski sadly passed away at about the time LIGO saw its first gravitational waves, and I have retired. It's now Yanbai Chen and Rana Adhikari at Caltech and the Brzezinski's successors in Moscow developing this quantum non-demolition technology to deal with this. But the key idea came from Carlton Caves, a graduate student and then a postdoc of mine in 1981. He said the key to controlling the quantum fluctuations of the jiggling of the center of mass of the mirrors is quantum fluctuations of light or of the vacuum. If you take a box and you remove everything from inside it, there are still left fluctuations of everything that could exist inside there, including light. And these quantum fluctuations of the light, then, are something that is always present. And Carl had the insight to realize that these quantum fluctuations of the light entering into the interferometer backwards from the output port would go in, they would beat against the laser light and cause and would start to manipulate the quantum fluctuations of the mirrors. And so if you were to manipulate these quantum fluctuations of light, the vacuum fluctuations, if you were to manipulate them by a technique called squeezing, which was largely developed by Jeff Kimball here at Caltech, independently of LIGO, if you could do that, manipulate those quantum fluctuations of the light before they went in, then those would manipulate the quantum fluctuations of the mirrors, and you could use that to do quantum non-demolition, to circumvent the noise due to these the bouncing around of these 40-kilogram particles. It's been 15 years of QND technology development to take these ideas and turn them into reality, but they are being installed in LIGO as I speak, and the first phase of this QND technology will be in LIGO when LIGO turns back on, makes observations in April. Then there was the issue of sources of gravitational waves. Already in 1980, I thought that the strongest sources would be colliding black holes, and I knew that to learn the wave's details, we would have to have computer simulations that would calculate the shapes of the waves, or the waveforms, for comparison with observations in order to interpret the signals that we see. In the early 2000s, so the community of people working on numerical relativity to do these simulations got a big boost from us saying we really need these simulations of colliding black holes for LIGO. By the early 2000s, I became alarmed because the progress was not good. And so I, at that point, left day-to-day involvement with LIGO to co-found, together with Saul Tucholsky, who was at Cornell at the time, the collaboration to simulate extreme space-times, extreme being colliding black holes in this case. Private funding was essential because NSF would not grant us the necessary funds to build a large enough research group to pull this off. Things were stymied because these research groups that were trying to do it were too small. They didn't really have a critical mass. And so once again, Walter Burke and the Sherman Fairchild Foundation stepped up to the plate, as they have on a number of occasions for us here at Caltech. And with that funding then, at about level of about $1 million a year since about 2004, we took off. The first successful simulations were done by Franz Pretorius in my research group here at Caltech as part of the SXS collaboration. We brought Saul Tucholsky here now half-time, so he's half-time here and half-time Cornell, leading the combined effort with a number of other institutions having joined in. By 2014, the simulations were mature enough for Advanced LIGO's first gravitational wave searches. And so the discovery came in September 14, 2015. And I show here a movie of the two black holes that produced the gravitational waves that we first discovered, a movie produced by Saul Tucholsky's SXS collaboration, or more precisely by 3 of his Cornell students. And I'll tell you the story of these waves. 1.3 billion years ago, when here on Earth, multicell life was just forming and spreading over the globe, but in a galaxy far, far away, 2 black holes circle around and around each other. emitting gravitational waves, and as they lost energy to gravitational waves, spiraling together. These are the shadows of the black holes against the field of stars behind. The black holes got closer and closer and closer. Then they came crashing together in a gigantic cataclysm that doesn't look that spectacular here, but a cataclysm so humongous that it did the same thing as if you had taken 3 suns, completely annihilated them, and turned all of their energy into gravitational waves. 3 solar masses of gravitational wave energy came flying out as gravitational wave burst from the galaxy in which those black holes lived into the great reaches of intergalactic space. Across intergalactic space, they arrived at our Milky Way galaxy 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. For 50,000 years, they traveled through our Milky Way. They arrived at the Antarctic Peninsula on 14 September 2015, 3 days before LIGO's advanced detectors were scheduled to start their first gravity wave search. Fortunately, they were turned on. They were in the process of tuning them to prepare for that first gravity wave search. The waves traveled up through the Earth unscathed by all the matter in the Earth, emerged at our LIGO gravity wave detector in Livingston, Louisiana. 7 milliseconds later, emerged at the gravity wave detector in Hanford, Washington. They shook the mirrors in those detectors by this minuscule amount that was predicted, 1/100th the diameter of the nucleus of an atom. The signal was captured then by light with photodetectors and then fed into computers, and the computers then spewed out results, and the humans looked at the results. And then the signal was too strong, too good to be true, and so the whole team went in for several months looking at these huge number of data channels that would tell you about anything that might be going wrong. There was nothing going wrong, no sign of anything going wrong, and ultimately there was an agreement within the collaboration. Gravitational waves had been seen. So 5 months later, what was then the 1,000-person LIGO collaboration with some contributions from a team called Virgo in Europe, this team made absolutely sure this was real and announced the result to the world. And the result, when they signal cleaned up, which is shown here in gray, was superimposed on the predictions of the SXS numerical relativity collaboration. And the masses and the spins of the black holes were tuned in the numerical relativity simulations until you got a near perfect match. The conclusion was that this was an initial of black holes, 29 solar mass black hole and 36 solar mass black hole, a total of 65 solar masses. Collided and merged, formed a 62 solar mass black hole at a distance 1.3 billion light years from Earth. And that was then the movie that I showed to you. And this was the newspaper accounts, the front page headlines in newspapers around the world. For me, much more interesting was to see what did that collision look like in terms of the warped space-time. And we can visualize this then by looking in from a higher dimension, as I did before, and you see the 2 funnels that are the black hole shapes of space. You see the color coding that is the slowing of time. You see arrows that are dragging space into motion. And this is the movie that was made by the SXS team to show the collision as seen from the bulk. A gigantic wave, like a gigantic splash in a storm at sea, going up. We pause this at the moment of collision, then it oscillates, and the oscillations die out, and 3 solar masses of gravitational wave energy go traveling on out. This then, for me, was tremendously exciting. It was the beginning of what John Wheeler called geometrodynamics, actually seeing the dynamical behavior of warped space-time in the equivalent of a storm at sea. And that's the one research area that I continue to pursue in collaboration with members of Saul Tukulski's SXS team. LIGO has now seen 10 black hole collisions, 1 neutron star collision. By the 2030s, it will likely see waves 20 times weaker than what it now sees. We'll be seeing every black hole collision in the universe with masses less than about 100 solar masses, and a variety of other warp side phenomena. Also, by the 2030s, We will have other kinds of detectors in 3 other frequency bands. We'll be seeing gravitational waves with periods of oscillation of milliseconds, with LIGO and its international partners, with an analog of LIGO in space called LISA, and later the Big Bang Observatory. We'll see gravitational waves with periods of minutes to hours. A technique called pulsar timing arrays. We'll see gravitational waves with periods of years to decades, and a technique called CMB polarization, gravitational waves with periods of hundreds of millions to billions of years. Now, of course, that's a bit longer than a graduate student lifetime, so you don't sit here and watch the oscillations, but you see a pattern on the sky that's produced by primordial gravitational waves from the Big Bang. And in fact, we expect to be seeing gravitational waves from the Big Bang with 2 of these types of detectors by the 2030s, with one of them probably by the 2020s, and the other one maybe by the 2050s, actually exploring the birth of the universe, gravitational waves from the birth of the universe. Well, I have overstayed my welcome. I was going to also tell you about wormholes and time travel, but I think that the evening is getting late, and so I'm going to give you a quick verbal summary of that. What I've told you is the most exciting work that I have been pursuing in my career. But there was a period in the late 1980s and early 1990s when we were pushing to get LIGO funded, a period when Robbie was fighting battles in Congress to get things funded. And things were slower than they had been on LIGO. And I had a phone call from Carl Sagan, a dear friend, astrophysicist friend at Cornell, saying, would you give me advice about a novel I've written called Contact, which I'm also planning to turn into a movie. And I said, sure. And it turned out he had his heroine traveling through a black hole to get to the center of our galaxy, to get to the star Vega. And I responded to him. I said, you can't do that. She'll die. You have to send her through a wormhole instead. And so I went back and resurrected the idea of wormhole, which had been very popular and near and dear to the hearts of Einstein, Hermann Weyl, and John Wheeler in the period before John Wheeler in 1960 and Martin Kruskal discovered that wormholes will self-destruct if you don't do something to hold them open. And so these wormholes, things that are links between this region of space and that region of space, you go in here, you can come out there, you can look at something that looks like a crystal ball here, and you see light coming from over there. But over there might be the other side of the universe, and here might be here. So anyway, these wormholes then became, for me, just because of the call from Carl Sagan, a subject of interesting research. And then I quickly, together with some students at Caltech, I discovered if you could have a wormhole, then you could turn it into a time machine by use of some phenomena called the twins paradox. And so I then, together with students and colleagues, and then a number of colleagues at other institutions, began to develop the research on the theory of wormholes and of time travel. When we came to the crucial point where we were having trouble getting funding for LIGO from Congress, Richard Isaacson, who was the superb program director for gravitational physics at NSF, and was the source of funding both for my work on wormholes and time travel and for LIGO. He came to me and he said, I'm afraid that Congressman Dingell and others in Congress may come and get on our backs because you're doing this wormhole and time travel research, and that might affect LIGO. So I think maybe you had better cease using NSF money for the wormhole and time travel research. Even though it's really important, we could have trouble with Congress. Fortunately, Caltech stepped up to the plate again. And I had money then from a Richard P. Feyman research fund to continue this crazy research. It was not really totally crazy research because to me, I came to realize that by asking questions like, can you build wormholes for fast interstellar travel and time machines for going backward in time, even though we can't do experiments with them, by asking the laws of physics deep questions of this sort, you can learn things about the laws of physics. It sets your mind, enables your mind to focus on particular aspects of the laws of physics that are really important. And so this became a way to learn deep things about the nature of time and space from the laws of physics. And the bottom line is that you probably cannot have wormholes, but we were not able to prove that for sure. The bottom line is that whenever you try to build a time machine, even if you're an infinitely advanced civilization, that time machine will probably self-destruct at just the moment you try to activate it. We don't know for sure. The answers are held tightly in the grips of these laws of quantum gravity that we don't understand. But that was a lovely interlude for me in the period when we were having trouble getting LIGO funded. The moment LIGO was funded, all that research went by the way for me, but I have colleagues at other institutions who continued to pursue it, and I focused in on LIGO. And so there is some sense of my career here at Caltech. I'd like to just conclude by saying that Caltech has been a marvelous place. I can't imagine any place better to build a career. I have had the benefit of wonderful colleagues, scientist colleagues on the faculty, superb students and postdocs, a wonderful administration that backs you to the hilt when you want to do something that's really important, even if it sounds crazy, if you can make the case that you have a shot at it. Staff that are really superb at helping make things function and helping us achieve our dreams. Trustees and friends of Caltech who give us great support and great advice. It is just the ideal place to do a career, to have a career like mine. And I was never tempted for 1 minute to leave once I came here on the faculty. Thank you.